AB Cactus BC, Unit 8, Day 8, Office Hours. These are the answers. Pause the video if you need to check your answers. Okay, assuming you've checked them, let's try them out. So first one, what is the sum of series? Now, the only kind of series that we know how to find the sum of is geometric series. And so we got to confirm it's being multiplied by -1/4. -1/4. Not 3. 3 stays the same on top. So I think it's -1/4. And it's alternating signs. So it's got to have a negative in it. So it is a geometric series. And the A value is 3/2. The R value is -1/4. You want to make sure that the absolute value of the R value is less than 1, which it is, which means it converges. So we can use the formula that you should memorize for the sum, A over 1 minus R, 3/2 over 1 minus -1/4. Be careful. So 3/2 over 5/4, 3/2 times 4/5, 6/5 for the final answer, 6/5. There you go. All right, next one. Taylor series centered at x equals 0, so that's a Maclaurin series. Now we can use those memorized versions because. So I mean, I would just write it down. This will help you just make sure you remember it, but it also help make sure you plug things in the right spots and don't mess it up. So sine is all the odd terms of the e to the x series, but it's also alternating. So x to the first over 1 factorial, x cubed over 3 factorial, x to the fifth over 5 factorial. And it keeps going. Now, we're trying to find the pattern here. So we need to come up with the nth term, -1 to the n. Now, it depends on if we start at 0 or what we start at. X to the, so if we start at, all of these start at 0, well, most of them except for this one. But I'll start with that. And they have k in, same thing. But I don't memorize I memorize this open form because it's an easy pattern. But trying to memorize the nth term, I think, would just be too complicated. I think it's easier to just 2 times plus 1, 2 times plus 1, 2 times plus 1. 2n plus 1. Same thing on the bottom. 2n plus 1 needs to be in parentheses, factorial. So that's a sine series. So if we do sine x squared, then we're just going to plug x squared in everywhere we see an x. Now, it needs to be in parentheses. And we might be able to get away with just not having to try and figure out the pattern again if we plug it into our pattern. So x squared okay, and that's going to give you x to the 4n plus 2, rules of exponents. And then if we're going to do sine x squared divided by x squared, then we could simply just divide this all by x squared. So that's going to give you a 1 for the first term. This is x to the 6th, so it's going to be minus x to the 4th over 3 factorial. This is x to the 10th, so it's going to be plus x to the 8th over 5 factorial. And I think it's worth it to keep track of the pattern because I think it's a lot easier to figure out the pattern on that first one and then just make changes to it. So this is going to be x to the 4n because it's plus 2, but then we subtract 2. So we're looking for the one that n equals 0 to infinity, -1 to the n, x to the 4n over 2n plus 1, parentheses, factorial. If we start at 0, and right there, e. Now it's possible they could put the first term and then make it start at k equals 1, and then it would probably be the same formula. Like if we had the first term here, but that doesn't make sense here. If we did 1 plus that would also work. So you got to watch out on multiple choice. Sometimes they try and throw creative things at you. Okay, number 3, they just give you a closed series and ask you what does it equal, which is they're asking you to try to find the sum. So this, you see sine in there, you're like, oh, we should do that. No, sine of pi over 6 is a constant number. Okay, what's sine of pi over 6? Sine of pi over 6 is 1/2. So this is the same thing as just a 1/2 being in there. There's no variable inside. It's always 1/2 no matter what. The k is not involved inside. So this is really just a geometric series. First term is 1/2, next term is 1/4, next term is 1/8. Or actually, first term is 1. So this is a geometric series. And you might be like, but that's all we ever deal with is geometric series. Okay, but next chapter, we're going to learn a bunch more series. And geometric series will still be part of it. So I think it's good to just practice identifying them by name, because the different types of series will have different types of procedures and ways of dealing with them. A equals 1, R equals 1/2. You got to make sure that the absolute value of R is less than 1. Make sure it converges. If it doesn't, answer E is an option this time, right? So got to watch out. Some people won't even think about it. This formula, S equals A over 1 minus R, will still give you a number if you apply it to a series that doesn't converge. It doesn't make sense that you're using that formula, but it'll give you a number, and I bet that number will be in the list of multiple choice answers. So 2. Now, some of these other ones are based off of probably, this one's if you make the mistake of thinking that sine of pi over 6 equals root 3 over 2. So if you don't know your trig, you're going to get the wrong answer on this, even if you know your calculus, unfortunately. You got to be good at trig to get your calculus answers correct. Okay. So this one says the first 3 non-zero terms in the Taylor series about x equals 0, which is the Maclaurin series, for this function. Now, you could do it the long way and build the Taylor series, okay? But we know e to the x, so we have that one memorized. It's 1 plus x to the first over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, and on and on and on, right? So e to the negative x, we would just plug a negative in. And this is a Maclaurin series, so this only applies because this one's centered about 0. You plug a negative in everywhere you see an x. You can plug a negative x in. And that's going to give you 1 minus x plus x squared over 2 factorial. It essentially changes the e to the x series into an alternating series. And then you're going to just distribute an x into all of it. So x e to the negative x equals x minus x squared plus x cubed over 3 factorial minus x to the 4th over 4 factorial. And we want the first 3 non-zero terms. So x minus x squared plus, this should have a 2. Gosh, dang it, I almost messed up. Okay, good thing that wasn't on there. But it's answer D. Now some of these, here you have the negatives wrong. Here you totally forgot the negatives. Here you made them all negative except for the first term. So these are all based off of very common mistakes. This is you forgot to do the last step. That was our second answer. Okay, next one. We have a closed series and we want to know what it equals. Well, that means you're trying to find the sum of it. And the only way we know how to do that is for geometric series. Unless it fits one of those other special power series. This is called a number series because there's no x's in it. So the only way we know how to find the sum of a number series is geometric series. So if you plug 1 in, by the way, the first term is 1/4, and then the next one's going to be 1. If you plug 2 in, so this is a little different. You might think the r value is 1/2, but the r value is not 1/2 because you plug 2 in, it's going to be 1/2 to the 4th power, which is 1/16, and it keeps going. So this is the same thing. Sometimes it's worth trying to simplify what's in here. It's 1/2 squared and then to the n. Like you could do that, right? So this is 1/4 to the n. And it starts at n equals 1. So the first term isn't 1. The first term is 1/4. So a equals 1/4. R equals 1/4. Let's make sure that the absolute value of r is less than 1. I'm going to make you do that on the test before you start using that sum formula to let me know that you actually know that you can't just use it all the time and that you figured it out. This is all the work you'd have to show on the test to get full credit for this kind of problem. That won't be multiple choice on the test. The algebra, I guess it's up to you. I would hate to make a mistake because I did too much algebra in my head and saved not that much time. The answer is 1/3. E is for the one that diverges. So if this ended up not being less than 1, we would have picked answer E because it blows up. Okay, number 6, they give you this function and then they say to take the derivative of it. Well, you can simply take the derivative of this. Anything within, don't treat n like a variable. So -1 to the n plus 1 is just whether the term is going to be positive or negative, which if you take a derivative, it's still going to be positive or negative. The stuff with the x, that's where the derivative comes in. So the derivative, this power rule, you multiply it in front, and then you decrease it by 1, right? And the bottom's still the same. So that is it, but we probably want to clean it up. I'm assuming the answers are cleaned up. So check this out. 2n plus 1 factorial is the same thing as 2n plus 1 times the next lower factorial, which should be 2n factorial. And then you can cancel those out. So that might be all we can do here. You need parentheses around the 2n. Otherwise, the factorial is applied to what is directly next to, kind of like an exponent. So we're looking for -1 to n plus 1, x to 2n, 2n. There it is. Okay. So you can take derivatives of the nth term in closed form and get the new closed form directly. This one, again, we're trying to find what it equals, so that would be the sum. We can just plug in some numbers just to see what's happening, just to make sure we get the first term. So if you plug 0 in, you get 1, and then this is a geometric series. All right, so this is a geometric series. So if it's geometric, I think it's good to write it down. Next chapter, that'll make that much more easy when we add a bunch of other series in that aren't geometric. A equals 1, r equals -pi/3. We need to make sure that the absolute value of r is less than 1, which it is not. Pi is 3.14. That's bigger than 1. This diverges. But I guarantee these answers are based off the people who decided to go ahead and say, oh, yeah, the sum equals a over 1 minus r, and a is 1, and r is -pi/3. So it's going to be 1 over 1 plus pi/3. Yeah, we could clean it up, possibly. It looks like some of the answers are cleaned up. and go with this answer. But that formula does not make sense for a diverging series. So hopefully we learned a lesson there. You got to check every time. On the test, I'm going to require you to check. Otherwise, I'm going to assume you forgot and got lucky, and I don't get points for luck. Okay. This problem seems clearly like we probably use graphing calculator, which I've noted here, because it's got these crazy, very small decimal answers. That would probably be very hard to do. Let E be the error in the Taylor polynomial used to approximate this function at this value. Okay, so this is a Taylor polynomial. It's a truncated Taylor series. And the error anytime is going to be equal to the actual function minus the estimate. And, probably absolute value of that. And this is something you're going to start to see a lot more, especially on like free response problems. If you might just see this and say, oh, they're talking about the error, right? That's the error. The difference between the actual value and the estimate is the error, how far off it is. So that's going to be sine of 0.5, and we can use the graphing calculator, minus, and we're going to plug 0.5 into this. Wherever we see x, that's going to be the estimate. If we took the infinite terms, it should approach the actual value. So on my calculator, I'm going to say sine of 0.5 minus 0.5 minus 0.5 to the third power divided by 6. And I get 2.5888719 times 10 to the negative fourth, which is, I think it's going to be easier if I write it in regular notation, not scientific. I'm going to move the decimal over 4 spots. So 3 zeros after the decimal point. So that is the error, and we're trying to figure out what it's between. So it's definitely smaller than this. It's not less than 0.001 either way. This looks like the right one. It is bigger than 0.001 and less than 0.003. I mean, that's the one that's closest. It's not bigger than 0.005. It's not bigger than 0.07. So, an interesting question. All right. But that's error. Simple idea. Actual value minus estimated. Okay. Number 9, the Taylor series of a function f at x equals 3 about. That means the center. That's a value. They say about. Like not like approximately about, like around is what they mean, like nearby, about, with it in the center. So they give us this series and they said, what's the value of f triple prime 3? So that's the third derivative, which we know has to be connected to the term with the third power and the third factorial, right? Because that's how a Taylor series is. So we know that 7x minus 3 to the third power over 3 factorial, the way we would calculate that is we'd find the third derivative at the center, x minus 3 to the third power over 3 factorial. So if we use this, say, okay, well, we're trying to find this. I can divide this out of both sides. I can divide this out of both sides. So it has to equal 7. That's it. Okay. Excuse me. All right. That's the way you do it. Okay. Next one says, to what number does the sequence converge? So to what number does the sequence converge? This is the nth term. Okay. So this is a sequence, by the way, not a series. So we're not looking at the sum of all the terms. We really just want to know what do the terms themselves go to. So this is the question. I know that we haven't seen anything really like this yet, but that's what's going on here. And this is the notation for sequences, is curly braces. This is really just a limit question. So I'm thinking what we might want to do is try to clean this up first. I mean, that's a really complicated expression. A to the n plus 2, rules of exponents, they have the same base. That would just be 8 to the 2, right? So, I mean, quickly, I would write it 8 minus n to the 200 over 3 minus n squared to the 100, and 1 over 64. I'm just trying to help myself here. I think these have two different powers. If I could put them into the same exponent, it'd be a lot easier. And so what we could do is we could say, well, 8 minus n to the 200 is 8 minus n to the 2 and then to the 100. So I'm doing a lot of algebra right now. I'm not doing so if I do that, then I could go ahead and FOIL that. That's going to be 64 minus 16n plus n squared over 3 minus n squared. Now it's all to the 100th power. Okay, I think that's going to be a little easier to work with. Because now I can take the limit of what's inside. And the dominant terms are n squared and negative n squared. So that's going to go to the ratio of their coefficients, which is negative 1 to the 100th power then afterwards, which makes it positive, which gives you 1 over 64. So this really didn't use any knowledge really so much. I mean, the work that we had to do had nothing to do with work we've been doing in this chapter. It's just a lot of algebra and a simple limit in the end. Okay. Now, by the way, this series, if we were to add all the terms up instead of the sequence, if we were to treat a series, the fact that the terms go to 1 over 64 and don't go to 0, they have to go to 0 to have any hope of converging, means that series would diverge for sure. Okay, let f of x be the function whose Taylor series converges for all x. Okay, Taylor series. If the nth derivative is less than 1, that right there makes me think I'm probably going to do Lagrange error bound, because they're giving me information about all the derivatives, very vague, but they give me an upper ceiling on, where f to the n x is the nth derivative of x. What is the minimum number of terms for the Taylor series centered at x equals 1 necessary to approximate f of 1.2 with error less than 0.001. You can use a calculator on here because you're gonna. So essentially, we're trying to find the Lagrange error bound. We're trying to force a Lagrange error bound to be less than this. So Lagrange error bound is the absolute value of the f plus n plus 1 derivative at some value c, x minus a, to the n plus 1 over n plus 1 factorial. I'd challenge yourself to write that down from memory every time and write it down. It'll help you memorize it and it'll help you make sure you put things in the right spot. For us, we know, let's put in the information we have. We know this right here. Well, all we know is that we can put a 1 there. That's the maximum it could be, okay? We're evaluating it at, now it's centered at x equals 1. So, but we're going to evaluate it at f.2, 1.2. So the x value is 1.2. The center is at 1 to the n plus 1 power over n plus 1 factorial. And so that's just going to be 0.2. I mean, we could write this even simpler. It's going to be 0.2. And we could drop the absolute values because we know it's going to be positive at this point. So I've gotten it down to that. That's our Lagrange error bound for whatever n is. And so they don't even give you n equals 0, 1, or 2. So they don't give you first, second, or third order. So we're going to just start with n equals 3 and calculate what the max Lagrange error bound is. So we plug 3 in here. It's going to be 0.2 to the 4th over 4 factorial. So on my calculator, which keeps telling me its batteries are low. I guess I should change them. 4 divided by 4, math, PRB, oops, that's not what I want to do. 0.2 to the fourth divided by math. I got to put the 4 first, then math, then PRB, then factorial. Okay, so that's 6.666 times 10 to the negative fifth, which is 0.40. So is that less than 0.000? How many zeros are there? 4 zeros. So close, but not yet. So I'm almost thinking maybe the next one might work. Usually it seems like each one gets you at least an extra decimal of accuracy, and that would, I think, do it. So I'm going to take advantage of my previous thing and just do that. Now it's 2.666 times 10 to the negative 6. So you're going to move the decimal over 6 spots, which gives you 5 zeros, which is less than 4 zeros with 1. So n equals 4. Now if they said what order or what degree, it would be one more than that. It would, n equals 4 would be, well, yeah, I don't know, n equals 4. That would be the 4th degree. It'd be the same. It would match up. N equals 0. Yeah. Okay. All right. Let's go to the next one. It's good practice, kind of good review in the form of multiple choice. So let f of x be the function defined by the power series. Okay, so it's a power series, it has x in it. That's what makes it a power series. If it doesn't have x, just has n's and stuff, that's a number series. So that's a power series. It says let g prime equal f of x and g0 equals 2. So then g of x would equal what? Okay, so g prime equals f of x, and we're trying to find g. Okay, so if you have g prime equals f of x and you want to find g, you would integrate both sides and you would get g, right? So we got to integrate f of x. And so we could integrate the closed form of it. That would give you, now technically what we do is I think we put 0 to x and you put t's in here. Okay, so we would get 2t to the n plus 1 over n plus 1. Just a simple power rule. And then you plug. Now the reason they give us G02 is because there's like a plus C issue, and we got to make sure we find the right plus C. Right? If we plug 0 in, we get 0. So it's going to be 2x to the n plus 1 over n plus 1. Assume we're still starting at that. Plus c. So if we plug 0 in for x, then that would go to 0 plus c, and it should equal 2. So our c value is 2. So I think our final answer for g of x is going to be n equals 0 to infinity of 2x to the n plus 1 over n plus 1 plus 2. Now I see a bunch of these with 2's in them, and they have it in front. That's fine. This one doesn't make sense because it should be added. This one doesn't make sense because it's 4. Well, this one starts at n equals 1, so that could be it. Like if we were to rewrite this and start it at n equals 1, we would have to include the n equals 0 term as part of this like extra term being added. Well, actually, they have it starting at, they have that. So we could just rewrite this if we get rid of, if we start at 1, then this would be the same thing, and it would still need to be plus 2. But maybe someone thought if we plug n equals 0 in here, then we add the extra 2 to here to make it a 4. So that one's kind of tricky. But I think the one that matches up, oh, well, that's good, because all of these have n equals 1. So we were going to have to for sure, well, most of them except for this one. But that one is incorrect because it doesn't have the plus 2 in it. But this one's correct if you change it to n equals 1, which is what I did. Another option, though, is if we did it to n equals 1 and we kept it 2x to the n plus 1, then we're missing that first term. Plug 0 in is 2, and then this is another possible answer. So all the answers, most of the answers there are like really close. Okay. Number 13, let the repeating decimal, which statement is true? What does it equal? Which one of these does it equal? Now, we could use the trick. We could try, there's this trick in Calc AB we learned, but that's not going to really help us so much here. So I think the idea is we want to take this and maybe try and think of it as a geometric series, okay? Which that might be it. Or if we get the geometric series, it doesn't match that, then these are probably the sum, okay? So the first thing I think we need to do is try and rewrite this as a geometric series. Now it's repeating decimals, so here's the trick. These are the terms. You could write them as a fraction, which none of these answers have decimals. So this is 24 hundredths, right? And then the next term is 24 tenths, hundreds, thousandths, 10 thousandths. And the next term is tenths, hundreds, thousandths, 10 thousandths, 100 thousandths, millionths. So those are the terms. So if we the first term is 24 over 100, and the R value is 1 over 100, because we're just adding 2 zeros to the end of the previous one, which is the same as multiplying by 1 over 100. The absolute value of R is less than 1, so it converges. This is a geometric series. If we were writing closed form, starting n equals 0, I mean, they have k's, whatever, you could write k. You would have the R value, usually to the k minus 1, and then the a term in front. So you could do that. We could possibly rewrite this as combine the 1 over 100 into this. So that would be 24 1 over 100 to the k, which would make you want to pick this, except it starts at k equals 1. So if we were to write this with k equals 1, we would have to make sure that the power in the 100 gave us just 100. Gave us, yeah. So it'd have to be k. Oh, this should be, okay, let me think for a second. I think that's right. This doesn't match that, because this one should be k plus 1. Yeah, that's what it should be. So these all are the closed form. Okay, so it actually does look like it matches this. Now, it's actually could be multiple answers, right? So we might also need one of these other ones. So the sum equals a over 1 minus r, and the a value is 24 100ths, and the r value is 1 over 100. So we get 24 over 100 over 99 100ths equals 24 over 99. We reduce that to 8 over 33. That one works too. So this one I'm not really sure. I mean, it looks like maybe it's close to this. Like if you want to rewrite it like this, it looks like they multiplied the top and bottom by 100. Should be 24 over 100 minus 1. So that one's off. Okay, so 1 and 3. Those Roman numeral problems are tough. It's 3 problems in one. You got to get all 3 problems right to get the one problem right. Taylor series expansion. About the point a equals 2. Now, expansion I usually think is like open form, but I don't know. Expansion of 1 over x. So about the point, this is the center, so I don't think we can use any memorized formulas. So I think we just got to build it. So the 0th derivative, I think we got to get enough to determine the pattern. Luckily, these derivatives are pretty easy. This is x to the negative 1, right? Power rule. 2 over x cubed. Negative 6 over x to the 4th. Kind of looks like a factorial on top. You guys see that? I think it is factorial. Right? This looks like a 2 factorial, 3 factorial, 4 factorial. Not that I mean, yeah, that might be important. Okay, so then we're going to plug the center in. This is part of the coefficients of each term. And it might be good not to reduce that. Just to, because we got to figure out the pattern. And the top I've already identified as a factorial. So I got that pattern. The pattern on the bottom is just going to be 2 to whatever term it is, right? So, or 2 to whatever term plus 1. That's the 4th derivative. So this is like n equals 4, n equals 3, 2, n equals 1, n equals 0. I guess we should look at the answers. They all start at 0. So each term, if you were to build the Taylor polynomial, first one is going to be this value 1/2 times x minus 2 to the 0th power of 0 factorial minus 1/4, x minus 2 to the first power over 1 factorial. This shouldn't be negative. I don't know why I put a negative there. Plus 2/8, x minus 2 squared over 2 factorial plus minus 6 16ths, x minus 2 to the 3rd power over 3 factorial. So we got to figure out the pattern here. And I've already started working on the pattern. So I think if we start at 0, it's alternating. So we need -1 to the nth power. If we start at 0, that would make the first one positive. This right here looks like whatever n value factorial. so that's n factorial, over 2 to the n plus 1, right? Because that x ends up being a 2, right? To the n plus 1 times x minus 2 to the n power over the factorial on the bottom. That's just part of the Taylor series. It's going to be n factorial. So that, I think that's it. But we could probably clean it up. Like the n factorials are going to cancel. Alternatively, you could have reduced these, like, oh, well, the factorials just cancel each other out every time, and say, okay, well, those are gone, and just figure out the pattern from here. Which this time I think it would have been fine. So I think we're looking for this. -1 to the nth, x minus 2 to the nth over 2 into, it looks like it's the first one. And none of them start at 1. So some of these, if we'd started at n equals 1, let's see if we could just write it real quick. It'd be -1 to the n plus 1 or minus 1 to make sure the first term is positive, and then x minus 2 to the n minus 1 over 2 to the n. So this is another possible version, and I bet there's one on there that's like that, maybe. No, not really. Anyways. Okay. All right. Last one, 15. Taylor series. Taylor series. I guess we should have wrote Taylor series. You usually write a T for Taylor series, P for Taylor polynomial, whatever. Equals this sum. So the Taylor series, it would be the whole series, infinite series, and be exactly equal. What is the value of the 10th derivative at 3? And you use your graphing calculator to help you. Well, the 10th derivative is going to correspond to k equaling 10. Right? And we could just directly plug k equals 10 in here to get the 10th term, or the nth term. It's not necessarily the 10th term, because k equals 0 is the first term. So we plug that in there, we get 1/2 to the 10th power x minus 3 to the 10th over 10 factorial, and that should equal the 10th derivative at the center, x minus 3 to the 10th power over 10 factorial. Now, the fact that this factorial is right there, those would cancel each other out. And so the 10th derivative, when you plug 3 in, should be 1/2 to the 10th power, which is 0.5 to the 10th. 9.7656 times 10 to the -4th, which is 0.00030 zeros. Oh, they actually have it on here. Remember, I always round up. Well, I don't know. This is an error, so I guess you don't have to round up, but this one looks the closest. Otherwise, you could have just started writing the open form of this each term until you got to the 10th term. That would be a lot of work. But if you understand that if you plug k equals 10, you understand the 10th derivative should match up to the x minus the center to the 10th power over 10th factorial, which we see right here. So k equals 10 should give you that whole term that has the 10th derivative as part of it. So, okay. That's it.